Alrighty, section 7.1. Now what we want to do is look at this idea of orthogonality. Okay, and it's much like being perpendicular, but again, because vector spaces allow for more general notions of angles and that sort of thing, we use a different word. Perpendicular is a physical thing. I draw two lines to be perpendicular. That's physical. Orthogonality is a concept. And so what we do is we say two vectors x and y are orthogonal if x dot y is equal to 0. Now, so remember that we just had that x dot y is equal to the magnitude of x times the magnitude of y times the cosine of the angle between them. Well, now, if magnitude of x and the magnitude of y are both strictly greater than 0, then cosine theta equals 0 if x and y are orthogonal. Okay, so now, physically speaking, right, if we're in 2 dimensions or 3 dimensions or something like that, and cosine theta equals 0, right, cosine theta equals 0 implies that theta is equal to pi over 2, or 90 degrees. Perpendicular. Right, so in 2 dimensions, something like that, if we have non-zero vectors, then orthogonality and perpendicularity are exactly the same thing. Okay, there's 90 degrees between the vectors. However, orthogonality is a more general sort of idea because, note, the 0 vector is orthogonal, I keep wanting to put an A there, orthogonal to all vectors. Okay, because this definition of orthogonality never says x and y have to be greater than 0, and so if I take the dot product of 0 with some vector y, I get 0 times y1 plus 0 times y2, and I could keep going to more dimensions, but that's 0. So 0 is orthogonal to all vectors. Well, it's not perpendicular to all vectors. So you see, this is a more general concept. And similarly, from our example of integrable functions, what this is saying is that if the integral from 0 to 1 of f times g dx is equal to 0, then f is orthogonal to g. Okay, well, two functions, think about a couple of functions that I might have like a sine function, might have then like a cosine function doing something along those lines. Um, you know, what the idea of perpendicular makes no sense here. But we could have something like this. Okay, so certainly I could get two functions that I multiply together and get an answer of 0 for their integral from 0 to 1. And they wouldn't be perpendicular to each other, okay, but we would call them orthogonal. So orthogonal in the Rn space is basically perpendicular, except for the idea that the 0 vector is also orthogonal to all vectors. But as soon as we get out of this Euclidean space and into function spaces, that sort of thing, orthogonal, it's a good intuitive notion of perpendicularity, but it has nothing to do with reality. I mean, the functions are not perpendicular to each other. Okay, so these are, this is what it means to be orthogonal. Is simply, for us, for Rn, we get that the dot product is 0. So we're, up here. So the dot product is 0. Okay, now from that we get our theorem 7.1.3, which says, now they say just a 2 by 2 matrix, but in general, if P is a real n by n matrix, and P transpose P equals I, okay, that is P is an orthogonal matrix. Okay, that's our definition of orthogonal, is that the matrix times its transpose gives you the identity, or in other words, the transpose is its inverse. So if it's an orthogonal matrix, then the columns then the columns of P are, now here's a big word, orthonormal. Cool. Now, so what does that mean? Well, if, say, they use x's, so I'll use x's. If xi is column I, sorry, there we go, column I of P, then xi dot xi is equal to 1, and xi dot xj is equal to 0 for I not equal to j. Okay, so the columns are orthogonal to each other, and the vectors themselves, with themselves, they are unit vectors. Okay, so this is a unit vector. So they're unit vectors that are orthogonal to each other. And the proof of that really just looks at the idea of multiplying in matrices. So if this is P transpose and this is P, See, this is our x1, our x2 column, and so forth. This is x1 transpose, x2 transpose, and so forth. And so when I do this matrix multiplication, I get this matrix that the 1, 1 up here is x1 transpose dotted with x1, or x1 transpose time. Yeah, so actually, I really don't want to do both. I could either write it as x1 transpose x1 or x1 dot x1, but that's that entry. And that, in order for this to be the identity, that has to be 1. And any other entry here, this would be x1 dotted with x2, and so forth like that. Well, that's got to be 0. So that's got to be 0, that's got to be 1. And so you see that's where the diagonal has to be 1, and that will be xi dotted with xi. And the off diagonal elements all have to be 0, and all those come from the mixes of xi dot xj, where I and j are not the same. Okay, so that is this notion of orthogonality, and we'll call that video done.